So in this session, we're going to just talk about machine learning from a 30,000 feet high model. I'm not going to talk technology here today, but the whole idea is at the end of this talk, if you guys go back and read a paper on machine learning, you don't need a dictionary to understand what is written there. A lot of times people have a lot of misconceptions about what's there. They misinterpret certain things for something else. Those sort of things are what we want to avoid by doing this session. Quick show of hands, how many of you guys are developers here? Wow, good number. How many of you guys have dabbled in machine learning? The only one guy I had to be scared of. But that's Rupert, it's fine, good friend. But again, the agenda is, we're going to cover what's machine learning, how it's different from artificial intelligence, which kind of gets interchanged and used. Break down some of the buzzwords. Quite a few are there. This is a really hot topic today. So quite a few of those buzzwords, what they mean, and what you should understand when you see them in articles. Some of the Google tools that we have released lately, which allow you to kind of get into this field much easier and kind of apply them to the apps or solutions that you're building. And maybe how you can go ahead and improve your team towards the end of it. I'm not going to be talking about this guy. Whenever we talk about machine learning or artificial intelligence, okay, the doomsday and all the other theories come about, but we are not talking about it. We'll reserve it for another day. And in short, we'll try and understand some of the words, some of the concepts, so that when you read the more complicated stuff, you have the base ready for it. To start with, when you say machine learning, it's about a program that can actually learn from its experience. That experience could be data that you feed into it and the additional information that you provide to it. Again, it will also kind of change and it can adapt based on the new data that you provide to it. So as situations change, it's adapting to it. Very simple example to call out. If you were writing a tic-tac-toe game, okay, if you're telling it how to win, you're telling all the rules by which it wins, all the if loops and conditions you write into it, that's logical programming. That's what most of us are used to doing. That's what most of the programs that we work with actually work like. We give it the conditions to create the outcome. We also ensure that those outcomes are achievable repeatedly by running those rules again. In machine learning, if you were to do it, you are going to give it a collection of games. It will go through those games, understand what a win outcome is, what a loss outcome is, and what are the rules to win. And it will interpret by learning that through the input that you give. So in any machine learning system, you have two phases to it. One is a training phase where you're providing it information to understand all of these aspects. Second is the application phase where you're using that information or the model that you have developed to kind of apply to a problem that you're getting. So the training phase is something that we would do before you release your solution. And then you take the model that you've created and then apply to input from real world and then change it. There are multiple ways you can do it, so let's go down to some of them. Before we jump into that, why is it becoming such a popular buzzword right now? The reason there is there's real world large enough data sets now and technology to work with that. And machine learning requires a lot of data. 1,000 data points or 10,000 data points is not enough. It needs a lot of data. There are multiple factors like learning coefficients and things like that you alter in your machine learning algorithms, which makes it difficult if the errors will increase if you actually make them try to learn too fast with too little data. And that's why the training phase has to be something that you've got to take care of well. And now we have hardware. We have specialized hardware for it. We have computational capability for that. We're working with such large data sets. Most of these large data sets can't be even loaded into memory. They're so large that you have to use a streaming model to kind of get them working. So we have technology which is there. Advancement in hardware makes it well. We are also getting into the phase where problems that we solve require some of these sort of mechanisms and techniques. It can't be based on rules. If you were to make a machine learn how to play a game or navigate a maze, you cannot always rely on that, on rule-based systems. You want systems that adapt to the environment. And they're more efficient and sometimes more efficient in solving problems for us. And how is it different from AI? So when you talk about artificial intelligence, there's more aspect than just learning to it. Learning definitely is one aspect. An artificial intelligence system will learn from its environment, from its input, and it will also make cognitive decisions. It will be creative. There are additional aspects there, creativity, knowledge representation, rationalization. There are multiple things that it will do beyond just learning. So you can't treat all machine learning systems to be artificially intelligent. Don't make that analogy, artificial intelligence equal to machine learning, no. And again, another concept that people talk about is deep learning. Deep learning is one aspect of, or one type of machine learning. So artificial intelligence, machine learning, and deep learning are three different things. First thing to keep in your mind. So, and it's artificial intelligence is more complicated to achieve because it has more aspects to it. So let's go into the buzzwords. Three classifications that you'll most probably see all the time when you go and read papers is supervised learning, unsupervised learning, sometimes semi-supervised learning, or reinforcement learning. These are three large classifications of learning algorithms that we have right now. And a lot of focus is happening on these three, right? So let me just make this really simple. This is oversimplification in some extent, I'll be honest, but this will help understand the concept really well. In a supervised learning system, you're having a large data set, the input, along with the labels. You're giving it properties that along with the data, so that system could learn. The system would actually learn using the data plus the properties that you provide. And then when it creates a model for itself, it then goes ahead, and when you give an input, it will use that to classify. So a lot of this is task-oriented. So if you have a task-oriented system that you're building, supervised learning can be a good way of doing that. And again, neural networks, yes, can be used for something like this. Sparse support vector machines. There are many different types in which you can actually realize a supervised learning system. But to give a real-world example, if I were to do supervised learning to kind of identify alphabets, I will provide a lot of pictures of alphabets. If I'm learning from pixel data, if the machine is learning from pixel data, I'll provide a lot of pictures of alphabets written along with what alphabet is written. Because I'm labeling it. This is English, this is A, this is B, this is French, this is a different character. That is how I would provide. So that next time when the system, so when it learns, it has provided a large data set along with these labels. So that when you provide a completely new input, it can actually use the information it got earlier and then decide, oh, is this a French one, is it English, or is it another language, one property? And also say, oh, is it A or another character? So that's how supervised learning systems work. Is this clear enough? Is the space okay? Good. Moving on to the next one. Unsupervised learning is different. Unsupervised learning, you are not giving it patterns. So you are asking it to figure out the patterns and clusterings within the data that you're passing. You're giving a lot of data, but you're not giving it the additional labels. You're asking it to find the hidden patterns and then use these hidden patterns to classify or add properties to the new data that you're actually passing to it. So during the learning phase, you give it a lot of data, and it will actually create a model that can classify based on the properties of the data you gave. It infers those properties. Second, when you're in the real world, you give it actually an input, it actually uses that information, that model, to kind of give an output. So anything that is like data-driven, pictures, classifiers, those sort of things can be used in this model. And it is usually quite useful in pattern recognition and things like that. Reinforcement learning, this is like the most talked about algo lately. A good credit to AlphaGo for this when it actually did something amazing. Reinforcement learning is what it actually is. Reinforcement learning is similar to unsupervised learning, but whenever you actually give it an input and it actually does the right thing, you reinforce it by giving that data back through backpropagation. Backpropagation is very simple. It basically takes the data error. So if you are saying that, assume I am training a dog, that's a great example of reinforcement learning. I'm training a dog to kind of act on a certain task or an action that I'm providing. And I say sit, and when it sits, I give it a treat. That treat is a reinforcement. In neural network terms, if you look at it, what we do is we actually take your input, we run it through the network. Finally, when you actually have the right outcome or the error, you take that information and pass it back to adjust the weights in your network. So in neural network, basically, simple thing, I'm going to explain it with neural networks, which is one way of doing it. It basically is a layers of computation, and each layer has a weight that transfers to the next one. So based on the weight and the computation, it transfers to the next layer a certain data. And that's how you come to a final outcome. Now, when you're doing that, you can adjust the computation or you can adjust the weights. Computation usually is never adjusted. It's always the biases and weights that get adjusted. But based on the outcome, when you're training, you can actually backpropagate those errors or differences and ensure that you're getting closer to the outcome. Let me explain that with the help of example. I'll come back to that. Neural network, again, another buzzword that you might hear a lot of times. Neural network is how we mimic the brain's working. How your brain works is basically by creating synapses, networks of information transfer. When you're getting information, it actually connects and creates a certain network. When information is passed through it in a certain way, it creates an outcome. That's why we recognize things. So if you have seen a cat before, and you know that it's a cat, the next time you see it, the way you recognize it, even though it's not the same cat, is because when you run through it, it can classify itself and say, hey, that's the way. Neural networks is very similar. We have a set of computational nodes, which can be considered to be a nerve. Then the nerve ending, how it transfers to something else, can be considered to be a node. Each node has weights, and the computation has biases. These are two parameters that you would alter in order to get the right outcome. So we create a standard neural network. Just create a random neural network, assign random weights, and you pass data through it. It is not going to get an outcome correctly. But as it starts getting outcomes, if you backpropagate the errors down, like from one layer to the next layer, from the output to output minus 1 to output minus 2, then what happens is for the same input, you get a much better outcome. So if you're saying that your tolerance should be between 10 and 5, numerically, I'm just making it really simple. Numerically, the answer should be between 10 and 5 for this input, and you got 8, you're going to take, okay, the median, 7.5, 8, you're backpropagating that 0.5, and then you're going to backpropagate that error. And sometimes the errors go through a couple of layers of backpropagation, but at the end of it, when you give, you get 7.5. If you're outside the range, you give that difference. More network layers or more neurons will be affected, but at the end of the day, the right outcome comes in, it comes out the right way. So reinforcement learning is really, really strong. AlphaGo works like this. What it does is it actually learns from the pixels, understands how it learns, and then plays against itself every time, reinforcing when it wins. So two AlphaGo versions play with each other. Then it says, oh, I won. It will update its algorithm, and then continues to play again till if the second guy wins, that data is taken and updates. So a better version of it comes in over a period of time. In AlphaGo, I think they made it play 30 million times or something. So this requires a lot of runs for it to get to the right model. But once the right model is created from the training, they can be applied anywhere else. And that doesn't require all the same amount of computational resource. A simple neural network example, cat and dog. I don't know the fascination with cats, but YouTube is full of them. We assume we are creating a neural network which kind of identifies from a picture cats or dogs. This is how it might be. This is a deep neural network, which means there are multiple layers of neural networks. And like I said, the free input is given to the input layer. Then that activates a few neurons, goes to the next layer. That creates a different set of activations, goes to the next layer, and finally the outcome comes in. During the training phase, you will feed it a million pictures of cats and dogs and say, this is right, this is wrong. When you get the output, you say, oh, this is right, and you backpropagate. When a dog is identified as cat, you will actually backpropagate that error for it to correct itself. And that way, it will automatically ensure that when it comes in the next time, it actually understands it. So over a period of time, your neural network will start identifying everything correctly to a great extent. There will always be tolerances of error. It's not going to be like writing an if statement. If statements will always work as expected, but this one, if you give something a cat which looks like a dog, maybe it can get missed because of the parameters it's used. But this layered approach makes it really, really, really strong. In Google, most of our speech learning systems are about 30 layers. So there are 30 layers of networks of neurons that actually go in, and with thousands of nodes or 10,000s of nodes, a lot of them. So there some of them are complicated depending on how complex you're solving. Speech is a really hard problem to solve, so that's why it has such a large network to solve that. What is there from Google's side from it? From a machine learning perspective from Google, we actually have something called as a Google Brain team, which is a team which is specifically building tools for our researchers to use. And one of the things that the Brain team actually, when the Google Brain team actually were working, what they found was that there are 3 classifications of users for this. One is your researcher, who's really interested in building a new algorithm or a new computation model for something. Then you have somebody who's a data scientist who wants to take this algorithm, apply it to an interesting data set, and create an outcome for it, or create a model out of that. The first guy is creating algorithms which kind of computes in a certain way. So he might find a better way of backpropagating information, coming to a certain conclusion in half the time. That could be what the researcher would do. Now, taking that algorithm and applying it into a real-world problem with a real-world data set is what your data scientists are doing. A lot of the data scientists will actually take real-world data, use algorithms, and then convert into interesting information or models that can be applied in an application or a solution. Now, then the app developers are there. The app developers usually take these models and then apply it into a solution. They are the ones that feed an input and get an output and act on that. So there are these different classifications of people. One of the things that we wanted to kind of improve within Google was the fact that these three segments of people need to communicate better. And that's why the tools that we built around it, like TensorFlow, were built from the fact that they can actually perform these different tasks and they can transfer that information across these teams. Initially, some of our teams used it. Now there are hundreds of products in Google which use machine learning because people have started seeing the benefit of it, and there are more and more teams using machine learned data to kind of optimize or solve certain problems. And some of these tools and techniques have come in, and we built an infrastructure specifically for that. And that is something that is applicable. I mean, that's something you guys can also use. Again, from a TensorFlow perspective, this is one of the tools that we've open sourced. This is the most forked project from Google. So a lot of people are adding more data to it, more algorithms to it. This is a great start. If your team's actually starting off with something, this is a great start because this comes with a lot of the algorithms, a lot of the tool set that is required to make things simple. Rather than starting from building computational models, you have a set of libraries that allow you to do this way better. So if you're giving it to a data scientist or if you're giving it to the researcher side of things, this makes it really easy. The researcher can go ahead and change something in the model and then transfer that information straight off into to the research. I mean, researcher can transfer that same thing into the model and then pass it to the development team directly here. So this makes it really, really fast to do. Again, it can run on your laptop or desktop. It can again run on data centers if your data sets are large. You can train the model, even use it in Android, iOS, or even a Raspberry Pi for that matter. The models can be applied everywhere. This is not something completely on the server side of things. A lot of people have this misconception that, oh, machine learning, that's a lot of data. It will only work on server-side technology. No. There are a lot of tools that you have on your phones right now which anyway is using all this. The other company, the notable thing that we want to call out is DeepMind. This is an acquisition Google made in 2014. This company started in 2010. And they are specializing in reinforcement learning. There are a lot of nice papers that they publish. If you guys are interested in this area, you should read some of them. Lately, they published an article on how auxiliary tasks, there's a primary task for which the reinforcement learning is working, and there are auxiliary tasks, and how the auxiliary tasks can actually help speed up the whole training cycle. So you should check that paper out. I'll share a link with it later. But they are actually creating these solutions which are actually learning through experience. One of the things that they specialize is in general purpose algorithms. General purpose algorithms are slightly different. They're not tuned for one piece of information. So if I make it learn one type of game, the information that it figured out from there can be applied onto another game. So they are not for one specific purpose. It's not like, oh, this can play just chess. So if it can play Go, AlphaGo is specialized for Go, but it can use that information that it figured out from playing AlphaGo and use it to study another game now, way faster. So general purpose algorithms are very, very interesting. They are how human brains actually really try and, very similar to how our brains actually learn. We learn from all the information there and we correlate it with other things. So if you have learned one language, it's easier for you to learn another language because you use the same techniques that you found useful in the first language and you apply to the second one, right? Similar thing happens with general purpose algorithms. So this is a really interesting space that you should watch out. Quick question. When is the last time that you think you used machine learning? Counter-Strike, okay. When was the last time you played? Yesterday, okay, good. I like you already. What about the others? Do you think you use machine learning on a regular basis or solutions with it? These are some of them. Gmail. If you use Gmail today morning while you were traveling, yes, you used some part of it. Inbox, photos, Google Now, music recommendations from Play, all these are based on machine learning. This is just a small set of things that you might be using on your devices today. But the answer to the question I asked is, yeah, the last time I checked my phone. Because yes, at that point you might have used something from a model that is applied. The models were actually built on the servers, but they were applied on applications within, which are running on your devices. So this is another interesting example I wanted to call out. In this model, what we tried to do was we gave it a picture and we gave it a set of pictures, the second side, and asked it to apply the style to the first pictures, to the next input. The input is the first one, the training data was the second picture. And you see the outcome. That's what the computer automatically made after learning this. You can see that it's not a superimposition of the second picture on the first. It actually understood the style in which the second picture was drawn and then applied that style back. Imagine trying to create a filter like this with conventional programming. It's going to be very, very difficult. Imagine you created one and it was successful and you want to create a ton of filters like this. Because, yeah, you're making a ton of money because of that. How would it be if you're taking a lot of time programming it in rather than making a machine learn it? So these are sort of the problems where you actually would need machine learning to solve them more efficiently than how we would actually write it in code. What can you do today? One is identify the three types of people that you have in your orgs. Because in your organization, you would have different types of people. Some people would be really interested in using the library and getting a solution out. Some people would be really interested in building the algorithms. Some people would be really interested in kind of using the data and making mix-match the data and algorithms and kind of create a model. Now, from a complexity to effort perspective, you could use one of the standard APIs, like the Vision API that we have. It recognizes 1,000 or odd features, which you can use to make a solution, which is kind of the less, basically you're using a pre-trained model, and then you're making a solution out of that. There are Indian companies which are doing that. There's one company in Cochin, which I think Karan mentioned about earlier. They actually use that. The recipes, you can actually take a picture of vegetables in your fridge. You can open the fridge, take the picture, and it'll tell you what you can make out of that. It uses machine learning to understand the different vegetables or different ingredients that you have, and then creates recipes and searches for recipes with that, and then shows it to you, all in a flash. Imagine I have to input 20 vegetables that I have on a keyboard into a mobile app. How many times do you think I'll do it? Taking a picture? Fairly simple. Yeah, cooking is another problem, but at least getting the recipes is easy. So things like that are simple use cases, and they are seeing tremendous traction with this. And this is not something that they built yesterday. They built it for 2 years ago. And they've been training that model for the last couple of years. From what I know, about 18 months, they've been continuously updating their algorithms, and now they have a great accuracy on what they are actually pushing out there. And it's really fast. I've used it myself. You should try it out. It's really fast and it's really fun to do because you take a picture and you shake the phone, it tells you a set of recipes in a matter of seconds. If I were to actually do this myself, I'm going to take at least 1 minute to input all that thing. And that's just too painful. So there are a lot of ways in which you can improve users' experience on your solutions with this. The second one is basically have the interesting data that you have, add it to an algorithm and create a model. This takes a little more because if you're building a solution like an e-commerce solution, you have a lot of data that you have in terms of usage patterns and how people are buying patterns, interest, click-throughs, how much time people are spending. All this information can be added to models and then create a predictive algorithm out of that. But because that data, interesting data, is just with you, you can actually use that data and use some of these algorithms and then create models out of that. The last one is to create completely new algorithms for new problems. This is more complicated, but that's another space in which people can actually do work in ML. So you would usually see that your problem would fall into one of these categories. Most people would love the first one, standard solution, use an API, get an output. Yeah, but that's not always going to be there because the data sets might not be equivalent for you. You might need to do some fine tuning over a period of time. Now to start with, how do you get your team ready? You need to understand the fact that as agencies or as software companies, we can't really completely ignore this. This is not a fad. This is how a lot of the software is going to work. And it is not the future. It is today. It is a present. It's not the future. Because you see so many solutions using this. And so many other solutions which you might be using on a regular basis, not just Google solutions, but there are many other major players in India who's actually using a lot of machine learning to kind of give you better recommendations, surface up the right information to you at the right time. Even newsreaders are using it lately to kind of understand users' pattern and show the most interesting news to the user. So there are a lot of places which it's getting used right now. So solutions that you built will most probably need to leverage such technologies. So getting your team ready is definitely important. And again, start looking for these integration points. They don't come naturally because we tend to think in a certain way, the logical programming, procedural way. You need to start looking for points where you can integrate some of these. Have an awareness of what's there as standard APIs, and then kind of backtrack into say places where, hey, this is a place where I can introduce something really interesting. I've seen one where they show a picture and recognize how the person reacted to it, not when the user clicks it, just by facial recognition. Like, you don't like it, you like it. You smiled at it, this was funny. So they actually would tag all these additional information by showing through pictures. And that is done during the time you load into the actual solution. So you got that training data, your data loads takes 10 seconds to load your application or whatever solution that they're building. They didn't give you a spinner, instead they showed you pictures and made you react to those pictures. Such a nice way of collecting data. A simple way of actually training a model. You're getting the data to train your model at the end of the day. Where they're using it, I'm not exactly sure, but that is a nice way of doing it. Down to TensorFlow, there is this particular thing is a great starter. There is a ton of tutorials that we have. I'll talk about them as we go. And there also have an awareness, go back and be aware of what are the APIs that are there. If you want to add voice interactions to your application with context, look no further. There's API.any.ai, which is an acquisition again from Google, which allows you to add interactions. If you are interested, I can show you something that I coded over the weekend. It's really simple 10 lines of code gets you voice interactions on your application. Like, I have a newsreader, I said, okay, now I talk to it. I can say, okay, search for interesting Android articles. And it just goes automatically, figures out that I want Android articles, gets that. But at the same time, I don't have to always say search for, find, search, get me. It figures it out. So I don't really have to say train the user to talk like I have programmed the system. The user can say, in most cases, it's figuring it out, and the success rate is really high, at least from the analytics that I'm seeing so far. And I'm yet to see somebody talking something else. Where I've seen a little bit, it's a global app, so it's a little bit differences when somebody talks in their own language. When you say talk, they actually talk in like Portuguese or French, and then the system actually doesn't get that all right. But when you're speaking English, most people get that. This is a great way, right? A search, right? If you want to actually type in like a sign in, you want to type in your user ID or your email ID. That's such a cumbersome way of doing it. I mean, you've got to speak to it, right? And you say, oh, what's the latest information? Like you talk to Google now, Google Home, for instance. How many have seen the videos of Google Home? Interesting? What is the reaction? You can integrate into that system. How it actually talks to you is very similar to how, I mean, building something very similar, at least a rudimentary way of building that with the data set you have is straightforward with tools like any.ai. So you should explore that one. Things to explore. One is the TensorFlow tutorial set. There is things for beginners, there are things for experts. If you want to actually have code labs, there are code labs as well as videos. So you can actually go ahead and make your teams use some of this, go through the tutorial, get your team ready, get them a better understanding of the system. Then the code labs as well as the videos kind of help you speed up things. The code lab, this particular one called TensorFlow Poets, is very nice. It's image recognition. The existing system understands a lot of things, but then you can actually train it with new data sets and then start applying that model to it. One example that I've seen is in TensorFlow Mobile, where you're applying that data into a mobile application, where they actually did show it a lot of pictures of paintings. And then when it's a museum app, so you go to the museum and you show your phone to the painting and it gives you information about the painting. It recognizes the painting from the picture. No matter what angle, what lighting it is, it actually figures it out. Then it actually goes back and searches for information, additional information, and then presents you with that. Simple thing. Now, if I wanted to add 10 more pictures to it or 10 more new paintings to it, it knows how to classify these as paintings. It knows how to go and search for them. You don't really have to train those models extensively for that. Yeah, this is a set of tutorials that you guys have, which you guys can go ahead and run through. But the ML recipes is pretty interesting. There is a very nice talk called TensorFlow and Deep Learning Without a PhD. A colleague of ours have actually talked last year with this content. Brilliant talk, you should see it. Really interesting. He explains it with a little bit of math. I have not touched any code here so far. I don't intend to either. But this talk is really nice. You should actually go back and get your team to at least watch this. They will get new ideas. There's a little bit of mathematical background that you need when you're actually working with ML. So if your teams are not coming from that background, yes, they might see that as a blocker. It's not like using an API without understanding the math behind it. Here, you might need to understand a bit of the math. So that is something, matrix multiplication, things like that are part and parcel of how you write TensorFlow programs. Because matrix multiplication, bare minimum at least. And there are some best practices around it, which most of these tutorials cover as you go. So having your teams trained for these things is really important. And that's it from me today. I hope this makes it a little bit more clear, at least spark some interest in you guys to go back and tell your teams to explore some of these things. It is a really high level overview, I understand that, but since we don't have a real hardcore developer population here, I thought it'd be best that we keep it really abstract. And I'm really looking forward to seeing you guys build something exciting. And when you do, please let us know so that we can actually showcase it and talk about it more. Thank you.